Welcome back. This is Mr. Hassan's Maths channel, and I'm now answering question number 7 from the International A-Level Edexcel Pure Mathematics P1 paper from June/October 2020, and I'm going to answer part A first. Now, part A, here we have a curve which has the equation y equals 1 over 2 minus x, and we're asked to sketch the graph of the curve C, and on the sketch we're asked to show the coordinates of any asymptotes, so any points of intersection with the coordinate axes, and we must state clearly the equations of any asymptotes. Okay, so in a question like this, first of all, we need to look at the type of function we have, and we can see that this is very clearly a reciprocal function. Okay, it's not linear, it's not quadratic, it's not cubic, it's a reciprocal function because there is x in the denominator. So whenever you have x in the denominator, you're going to have asymptotes, as I mentioned here. And the asymptotes, there's vertical and there's horizontal asymptotes. Now the vertical asymptotes are always those which have the equation x equals whatever the denominator becomes 0 with. Okay, so if you have y equals 1 over x, we know that this has the type of shape. This is like, you say, the parent of all the asymptote of all the reciprocal functions. It has this type of shape. That's how 1 over x looks like. And we can see that the asymptotes are where x equals 0, which is the y-axis, and where y equals 0, which is the x-axis. Okay, these are the asymptotes. And the vertical asymptote, x equals 0, is basically whatever makes the denominator 0. So over here we can see when you have y equals 1 over 2 minus x, we know that when x equals 2, this is, y is undefined. Okay, because you'll have y equals 1 over 0, which is undefined. So therefore, x equals 2 is the vertical asymptote. Okay, the vertical asymptote. Asymptote. Okay, and the horizontal asymptote here is y equals 0, because when you put y equals 0 here, you try to solve the equation, you have 0 equals 1 over x. Of course, if you try to solve that, you're going to end up with 0 equals 1, which is nonsensical. It's called a contradiction. So therefore, here in this case, y equals 0 is an asymptote. And similarly, if you have y equals 1 over 2 minus x, and you put 0 instead of y, you'll also have something which is called a contradiction. So because of this, we can say when y equals 0, okay, x is undefined. And therefore we can say y equals 0 is an asymptote. So y equals 0 is also an asymptote. Okay, asymptote. Okay, and we can see here also that it's going to cross the y-axis when x equals 0. So we can say that the y-intercept, of course it won't have an x-intercept because it doesn't touch the x-axis, because y equals 0, which is the x-axis, is an asymptote. So the y-intercept is when x equals 0. So you have y equals 1 over 2 minus 0, which is a half. So we can see that it's going to cross the y-axis at a half and 0. Okay, so if we were to draw this graph, it will look something like this. Always draw your axes with a ruler. Okay, now we've already determined that the asymptote is x equals 2. Okay, so I know that there's an asymptote at x equals 2. Okay, so let's draw that here. Let's say this is x equals 2. And we also know there's another asymptote at y equals 0, which is this is the y-axis, this is the x-axis, and this is the line y equals 0. That's the other asymptote. Okay, and we also determined that it crosses the y-axis at a half. Okay, half 0. Okay, so now, as we said, y equals 1 over x, and here we got y equals 1 over 2 minus x. Now this would normally be in the first and the third quadrant. Okay, it would be like in these two quadrants here. But because there's a minus in front of the x, it's kind of reflected. So therefore, it's going to be, as we can see from the fact that it passes through a half on the y-axis, it's going to be in these two quadrants here. So it's going to look something like this. Okay, it will have that type of shape. Let me just adjust it slightly so it goes through there. Okay, so there we have the graph of y equals 1 over 2 minus x. Okay, so that's how you draw this graph. Now, I know that there's some of you, okay, now this is a side point for those people who will definitely get confused when they think of this in terms of transformations with your knowledge of P1. Okay, so some of you will think of this, and I'll just make this as a little side point here, because it's something which I'm sure that some of you will have a bit of confusion with, because the understanding of how to draw such a graph using transformations requires you to have a bit more understanding than what you learn in P1. Okay, so this is just by basically recognizing that it is a reciprocal graph, recognizing that it's got a minus in front of the x, so it's going to be like in the other two quadrants. Instead of these two, it's going to be those two, and recognizing how to find the asymptotes. The asymptote is when whatever makes the denominator 0. But if you think about it in terms of transformations, which of course you can do, then it requires a bit more understanding. So let's say we have f of x equals 1 over x as our parent function, which we know looks like this. Asymptotes being where x equals 0 and y equals 0. Those are the asymptotes here. Okay, so you have your asymptotes, which will be in these two places here. That's how it would look normally. Okay, now, when you think about the new function, which is 1 over 2 minus x, it's basically, this is what has happened. You replace the x with 2 minus x. That's how you get 1 over 2 minus x. Now this transformation here, if we think about it in terms of just purely transformations, then that's where you're going to have some problem. Okay, that's where you're going to have some problem, because if you think about what you've in terms of what you've learned in transformations, you'll say, okay, basically what's happened is this is like minus, this is like f, you can say minus x plus 2. Okay, so you might think of it as it's reflected in the x-axis, in the y-axis, sorry, because it's inside the function. So it's reflected in the y-axis. Okay, so instead of going here and here, it's going to go in these two places, which we know it does. But then you'll say you've added 2 inside the function, so it must move 2 spaces to the left. So according to what you might think that the asymptote now moves over here. The asymptote moves 2 spaces to the left because you're adding 2 inside the function, and that technically is correct in terms of its, you know, that's what happens when you add 2 inside the function. It moves 2 spaces to the left. So you might think of it like, it has to go over here, and in that case minus a half would be the y-intercept, and x equals minus 2 would be the asymptote, the vertical asymptote. But you can see x equals minus 2 is not the vertical asymptote, because if you put minus 2 in here, you get 1 over 4. It's not undefined. Okay, and the reason why that does not quite work, okay, the reason why it does not work is as follows. The reason is that when you're dealing with a transformation, a combination of transformations, then you have to do it in a particular order. Okay, and if the transformations are all inside the function, okay, you do the opposite of BIDMAS. Okay, so you deal with the addition part before the multiplication part, and the minus x is like you're multiplying the x values by minus 1 basically, all right, or the reciprocal of minus 1, which is minus 1. So here when you got plus 2, that means you have to go 2 spaces to the left. So the first thing we had to do actually before we did anything else is this: we have to move 2 spaces to the left. So the vertical asymptote goes to minus 2. That's the first thing that happens. And then you have to multiply all the x coordinates by minus 1 over 1, okay, which is minus 1. So that means all the x coordinates, they change their signs. So the asymptote ends up at 2. So this asymptote ends up as at 2. Okay, and this is basically, reflected in the x-axis. So instead of going like this, this is going to go like this. And this, instead of being over here, it's going to be over here. And that's how we end up with the sketch, the way it looks in our final answer. Okay, so that's how you would have to do it using transformations. And some of you might have tried doing it using transformations. Okay, and oops, I've just crossed off the wrong one. Silly me. That was a new one. I had to cross off this one. Oops. Had to cross off this one. That was a new one. Okay. So that's how it should look, and that's going to be a half. So that's how you can understand how to deal with this using transformations. Okay, and it's something which is outside of the scope of P1, and it's taught in P3. Okay, and so that's something that is important for you to realize, for those of you who try to do it using transformations. But in the question in P1, for something like this, it'd be better for you to just deal with it in terms of, okay, let's find the asymptotes by finding what values of x and y cause this equation to be undefined, and find the y-intercept by putting x equals 0, whatever, and then just drawing it accordingly, knowing that there's a minus 1 over x is in the other two quadrants that it normally is in, and so on. Okay, so using transformations, you can understand it this way, which is outside the scope of what you have learned in P1. Okay, now, so, just to reiterate a few more points as well. When you're drawing your curve, don't make it go back on itself. You will definitely lose marks. Don't let it touch the asymptotes. Okay, don't let it touch the asymptotes. It must be drawn in such a way that it doesn't touch the asymptotes, and the curves should not go back on themselves like this. Okay, try be careful about that, because they will definitely lose you marks if you draw it in that way. Okay, now for part B. It says here the line L has equation y equals 4x plus k, where k is a constant. It says given that L meets the curve C at 2 points, 2 distinct points, show that k squared plus 16k plus 48 is greater than 0. So we have to basically solve the equation, okay, where the curve and the line intersect. Now they intersect when you solve them simultaneously. So you have y equals 4x plus k, and you have y equals 1 over 2 minus x, and we have to solve these two equations simultaneously. So you can think about it, okay, let's make them equal to each other, or you can say let's substitute y, instead of y put 4x plus k, for example. So you can say 4x plus k is equal to 1 over 2 minus x. So we can just cross multiply, say 4x plus k times 2 minus x equals 1, and we can expand this. We're going to have 4x times 2, which is 8x, and 4x times minus x, which is minus 4x squared, and k times 2, which is plus 2k, and k times minus x, which is minus kx. And let's bring this on this side as well. You're going to get minus 1 equals 0. And now what I can do is I can simplify this. Let's make the x squared term positive, just to make life easier. So I'll change the sign of everything I see here. So this is going to give me 4x squared, and then I'm going to have minus 8x minus kx, sorry, plus 8, let me just do this properly, sorry. Just change the signs of everything. So you're going to have minus 8x plus 4x squared minus 2k plus kx plus 1 equals 0. So I'm going to get 4x squared. I'm going to have the x terms minus 8x plus kx and minus 2k plus 1 other constants. Okay, so let me just take out this. Let me take out this x. I'll have plus x times, and I can say k minus 8. That's kx minus 8x, that's correct. Minus 2k plus 1 equals 0. Now, if it has two distinct points, okay, where the curves meet, then this equation here represents where they meet. So when I solve this equation, I'm going to find the points where the curve and the line meet, because this is where the curve and the line, I've solved them simultaneously. So if there's two distinct points, then this will have two solutions. Now, if this has two distinct solutions, then we know that the discriminant, because it's a quadratic, b squared minus 4ac, must be greater than 0. So we can see here now quadratic a is equal to 4, b is in terms of k, which is k minus 8, and c also is in terms of k, which is basically 1 minus 2k. Okay, 1 minus 2k. So we can say that b squared minus 4ac has to be greater than 0. So we're going to have k minus 8 squared minus 4 times a, which is 4, times c, which is 1 minus 2k, has to be greater than 0 for this to have two solutions. Expanding, you get k squared minus 16k plus 64, and that's going to give you minus 16 times 1, which is minus 16, and minus 16 times minus 2k, which is plus 32k, is greater than 0. And we've got k squared, we've got minus 16k plus 32k, which is plus 16k, and 64 minus 16, which is plus 48, is greater than 0. And that's, I think, exactly what we are asked to show. K squared plus 16k plus 48 is equal to 0. Yes, that's exactly what we had to show. And then it says, hence find the possible, or the range of possible values for k. So even if you didn't know how to show this for parts for part B, for part C we can use what they gave us, and basically we have to find the values of k for which this is true. Okay, the values of k which solves this inequality will also, give us the possible values of k for which there will be two solutions. Okay, so now what we can do here is we can first of all find what's called the critical values. This is a quadratic inequality. So we find the critical values. The critical values are when k squared plus 16k plus 48 is equal to 0. So we have to factorize this. So think of two numbers multiplied to give you 48, and they add to give you 16. So you got 48 no times 2, 24 times 2 no times 3. You got 24 times 2 is 48 times 3, 16 times 3 no. You got times 4. You got 48, 12 times 4. That's 12 on 4. So you have k plus 12 and k plus 4 equals 0. So k equals negative 12 and k equals negative 4. So those are the critical values. So what I'm going to do is I'm going to draw a little sketch. I'll draw a little sketch here. I'm going to have k equals minus 4 and k equals minus 12. This is my k-axis. Okay, and I can see that this is a smiley face, and it's going to go through 48 here on this y-axis, you could say, and it's going to go like this. This is like the discriminant axis. Okay, so you can see that the k squared plus 16k plus 48 is greater than 0. It's above the k-axis. Okay, it'll give you positive values when it's above, when it's in this region over here. Okay, when it's in this region over here and this region over here. So we can see that's going to be true when k is less than minus 12 and when k is greater than minus 4. So those are the solutions. Where k is minus 12, k is less than minus 12, or k is greater than minus 4. That's where you're going to find the solutions to this. So the discriminant will be greater than 0 when k is less than minus 12, or when k is greater than minus 4, and those values of k will be the values which cause this. When k is less than minus 12 and greater than minus 4, then there will be two distinct solutions for these equations. Okay, they'll meet in two distinct places. So this sketch that I've drawn here is not a sketch of any of these graphs. This is a sketch of the discriminant of the equation formed when I found the intersection of these two graphs. So this is actually the discriminant. So this axis is like the discriminant axis, and this is the k axis, and we want to find when the discriminant is positive, when it's greater than 0. So it's from minus 12 onwards See, the minus 12 and the 4 are not included. 20 minus 12, behind minus 12 and above, less than minus 12 and above minus 4. So that's the answer to question number 7. Okay, I took a bit of time explaining, especially for part A, because of some confusion that I'm sure some students would have if they thought about this in terms of transformations. Part B was pretty much quite a standard, straightforward type of question. And there we have it. That's the answer to that question. Thank you for watching. Other questions which are to do with this topic of functions, graphs, and also quadratics. I guess this is a mixture of both. Will be found in the playlist that I'll put up over here. You will also have a playlist showing you the other questions from this particular paper. And on the top here, some card taking you to another P1 style paper. Thank you for watching, and I hope to see you soon.